I think it's okay when we start. It's nice to have a few people in the session which aren't afraid by the term NoSQL. It's a rather interesting topic because when I first heard the term NoSQL, I kind of thought, what's that? We are currently, it's a presentation of a case study, so some introduction on NoSQL, on Hadoop and HBase, but basically it's a case study discussing a project we are currently building. It's for sensor panels for inverters collecting sensor data. The main thing here is that we have to deal with a lot of data, really a lot of data. So that's basically why I want to talk about this one here. First, going into more detail, we have to rethink our situation a bit, because we are pretty good in relational database. I think we are pretty good in managing databases with, I don't know, up to 10 gigabytes, or I don't know what's the biggest database you have in use. The thing is that in this session, we have to think really big. Not big in the term what you think it is big, but really big. So just think about something like that. We are discussing here managing data in tera and petabytes. So we have to deal with a lot of resources with a cluster, with a data center. So it's just the other thinking, just the other world. Well, there's the agenda. First of all, I want to discuss the so-called new. It's not really new, but it's more and more discussed. It's the so-called big data trend. We're gonna discuss the scalability changes we have, challenges we have in the big data trend. I'm gonna give you an introduction on what products are currently available to manage tera and petabytes. And the last thing is that the project we are currently building is not entirely based on a NoSQL database. We have to find a way to use both technologies for certain reasons. In general, you can encounter that the data volume grows dramatically. Probably if you're in a business with point of sales systems or something like that, you probably won't see this data growth. But in systems, sensor data, storing sensor data, or Facebook or Google or whatever, they are in a business where they really have to store and to manage a lot of data. So the first question is, what is big? What is big? What is big for you? What's the biggest database you have out there in production? 10 giga, 4 giga, to 10. Okay, so okay. Well, it's basically it's really the answer to this question is basically it depends on the business and the technology you use to manage this data. So for instance, if you try to manage I don't know 10 gigabytes with text files, you're probably in trouble. So the thing is that, for instance, Google, Facebook, Yahoo, they are all managing petabytes of data. The thing here is, when we are talking about big data, that most of the data is unstructured or is semi-structured. So basically far away from our perfect normalized relational world we are used to. What does unstructured and semi-structured mean? Unstructured are regular, I don't know, text files or some kind of lick stream from web-based applications, or semi-structured is a typical use case for XML or something like that, or HTML. So pretty much you have to handle that data as well. When talking about big data, it's not just the volume. The volume is one important piece in this formula, but there are two others. Or basically, the volume is not only defined by the data volume in case of terabytes or gigabytes or something like that. It's for you, it could also be the number of records in a relational database system, the number of transactions per minute, per hour, per day, or the number of tables, files you have to manage with your technology. Another one is the velocity. The velocity is pretty much defined on the latency you want to access the data. So there are different occurrences here. Either you want to access the data in some kind of batch style, so I don't know, running each hour some kind of batch process. Other one is near time, real time. So near time is pretty much what you see in regular old systems. If you have point of sale system, someone anti-state, a Twitter state or something like that. And there's also streams. So if you think about some kind of financial ticker or something like that, if you're in the financial business, they really have to react very, very fast on a huge amount of data in a certain time, in a very short period of certain time. And the third one is about the rarity. It's basically the kind of data you want to store and to manage. The one is structured. I think in the relational world, we are really good in managing structured data. But as already said, we also have to deal with unstructured and semi-structured data, or a mix of all. So that's quite complicated. Well, there are typical application domains for if we are talking about big data is pretty much sensor networks. So if you're in a business to collect sensor data and you're trying to process sensor data and analyze sensor data, that's a very interesting area for big data. Another one is social networks like Facebook, search engines, healthcare to store, to manage medical images, patient records, science in general, they produce a lot of data, bioinformatics is one, financial services, and condition monitoring systems in general. So what scalability challenges do we have here? Well, basically, if we are talking about a relational database management system, what do you do if you have scalability issues? Probably the first thing, or one of the first thing, is to scale up, so-called scale up your database server, so make your existing server more powerful by adding faster or more CPUs, by adding more RAM, by adding fast I/O. It's not only at the server level, it's also in the application, for instance, to create indices, to optimize statements, possibly to partition data. It depends a bit on the relational product you are using, if it supports partitioning data. You probably will try to reduce network traffic. Especially in the data warehousing area, you probably will try to pre-aggregate data, so you don't have to query, to re-execute aggregate queries over and over again on a very large data set. So you probably will try to pre-aggregate data in some time. That's a bit against our perfect world from our normalized world. So you might be able to, or you probably will go into the direction to denormalize data, particular data, store it redundantly to avoid complex joins. And a very famous one is replication to somehow distribute the workload. So just to have identical copies of the database on several servers, and you have some kind of load balancer between the client and your database to balance the workload. The problem here is with relational databases in the big data area, when we are talking about terabytes, that this usually fails. All of that, this usually fails either due to technical issues or to licensing issues. So if you're if you can afford an Oracle real application cluster, then you probably will go the way anyway, but you're still stuck if you reach a certain limit here as well. So to manage big data, there's only one solution, in my opinion. It's scale out. Scale out means not having one fat server around some a cluster with a number of nodes sharing the same run, for instance, and processing data in parallel. That's a true story. Lucky me that it didn't happen to me. Basically, a real project started this way. They had good knowledge in a relational database system like MySQL. But MySQL isn't important here. It doesn't matter. It can be any relational database here. They started with a regular setup with a powerful database server. Business grow. They have been in the sensor data business as well. Business grow, data volume increased dramatically. So the well-experienced project team using MySQL pretty much has done the following. They have been using MySQL partitioning to spread the database onto several disks. Firebird doesn't have this because we only have a single database file, or if we have multiple files defining one database, you can influence where a particular database file goes onto which disk. So they started to partition the data. Then they thought, well, I'm not able to handle that with one server. So what they did, they started to replicate data to several machines to distribute the workload. And they also denormalized data to avoid complex joins. So that's the one part of the story. The next one is that they were pretty happy with the InnoDB storage engine because they somehow needed transaction support. But they more or less saw that transaction support isn't any possible anymore with this data volume. So basically, they removed transaction support by switching to another storage engine. So what they basically end up with, more or less, or even only one denormalized table. Data was spread across several machines and physical disks. The thing was with all the partitioning, replicating, and stuff, the thing got quite expensive and hard to maintain. So what they are now doing is using a NoSQL solution, which is a perfect fit to store a huge amount of data. Well, just a short introduction to NoSQL. NoSQL is a term for not only SQL. So there are different NoSQL implementations out there. Basically, you can differ from three. There are one which are specialized on storing documents. There are others specialized on storing key value pairs, and there are other databases out there which are extremely good in storing graph structures. So the thing with NoSQL solutions is that you can scale out very, very easily with disadvantages compared to relational systems we're gonna discuss a bit later. So basically what the project team did in this sensor data domain business was the switch to a distributed key value store implementation called HBase. It's a NoSQL database on top of a so-called product called Hadoop from Apache. All right. So this Apache Hadoop, it's an open source software for pretty much reliable, scalable, distributed computing. It consists of three things: common package, a common library, which all other stuff is based on. The two most important thing are Hadoop is or supports or has a distributed file system, so you can store. You have a file system which is spread across several nodes in the cluster, and you have a software framework, a MapReduce framework for processing a very large amount of data in a cluster. The idea is, in respect to what hardware is needed here, is that it run on so-called commodity hardware. This means that not a crappy hardware, not a fancy hardware. It's just, for instance, regular consumer disks or something like that, which are very, very cheap now. So that's the idea of storage. Hadoop is widely used in the meantime. Amazon, Facebook, Google, IBM, New York Times, PowerSet, Yahoo, and so on. So it's a rather stable system for managing large data in a cluster. The Hadoop project at Apache is a top-level project, so it's very, very important for Apache. There are other projects going on in this Hadoop universe. I don't want to discuss every piece here. I think the most important one is, as we see later on, is HBase. HBase is a scalable distributed database that supports structured data storage for very large tables. And there are others like Mahoo, if you are going into the area of data mining on very large data. There is Zookeeper, which is essential for using HBase. It's some kind of high-performance balancer coordination service for distributed applications. So there is a lot of stuff going on at Apache in respect to distributed computing, distributed processing. Well, that's basically the MapReduce framework of Apache. I also have a more technical slide, but I think this one is really easy to understand. So what you have is you have several nodes in a cluster, several data on each cluster. So what you basically do in the MapReduce framework, if you want to process a large set of data, is to basically run through a map phase. A map phase reads data from the distributed file system. It maps to and transforms it into your destination model. So you rather get something like that, and in a combine or in a reduce step, you're gonna make it so that the data you have read here, you combine that, for instance, if you want to aggregate data. So if you have in this area in the map phase here, very, very detailed values in respect to your sensor data, and you want to aggregate that, you're gonna go through a reduce and a combine step to calculate the aggregates. So that's pretty much what the MapReduce framework is. That's a bit of a more technical slide here. we have the distributed file system here with several data files, and so on. So it's gonna read from the disk on each node. So each node is running one or more methods which basically reads data, and the users are then responsible to combine the data which has been read from several nodes, and more or less the result what you get out here, you can, for instance, store it again in the distributed file system. You can generate the file. You can write the result, for instance, in a relational database system or something like that. So that's a very short description of the MapReduce framework. HBase on itself is an open source Java implementation of Google's big table idea, big tables concept. I think it has been first introduced in a scientific paper in 2006 or something like that. HBase is a non-relational distributed database. It's optimized to store sparse data, which means that if you ever store nulls, what we know from the relational world, it doesn't need any storage at all. So it's a column-oriented storage. It has some kind of multi-dimensional capabilities. It promises to be high available. It promises high performance. And the main thing is that it basically runs on top of the high available distributed file system of Apache Hadoop. So the goal is of HBase is pretty much managing billions of rows with millions of columns each row with thousands of versions. We're gonna see this a bit later what it means. Basically running petabytes across thousands of commodity servers. That's a high level overview of the architecture of HBase. I don't want to go into detail here. I just want to mention that you have the solid base here is the distributed file system with spread across several nodes in the cluster. And you have HBase on top of it with basically one region server per node on the cluster with one or several regions, which basically stores the data in case of store files. So that's a very high level overview. So what happens here if the client connects is it uses the zookeeper, the load balancer, the distribution service to connect to the HMaster, to the so-called HMaster. It negotiates some kind of what data he wants to see, and after that he directly communicates with the region server so that the master is out of the game here. The data model is quite interesting, especially for sense data, because what we have here, we rather know the relational model. The data model in HBase is something like that you have a row key, so-called row key. It's pretty much a primary key in the relational world. You have a column and a timestamp. The timestamp is some kind of version. So one row can have several versions. It's similar to from the term similar to then to Firebird. So with this three dimensions, we can address one cell, one value. And the column consists of a column family. So the column here consists of a column family and a so-called qualifier. So with the example here, with the table here, we have an HBase table with row key 1, and we have a predefined column family here, and the column family can hold many qualifiers, and pretty much an unlimited number of qualifiers, and you don't have to predefine the qualifiers you want to store compared to the relational model. In the relational model, you have to define the table and the attribute and something like that. So you don't have to do that in HBase. So this is very flexible. If new qualifiers, for instance, new sensor types are coming along, you don't have to change the data model. So you just put into a new qualifier with the value you have done. So, and there's also the timestamp. The timestamp is pretty much an internal timestamp, which is a timestamp so you can address one particular value. So if you're interested in the most recent values, the most recent version of the qualifier values, and you don't provide a timestamp here when you query the data, you pretty much get this one here. So this root here. So if you add a timestamp here, then you can basically restrict the version you want to see of a particular row. The thing here is if you have null here, that's one of the thing of HBase. It doesn't need any space at all. So it's very efficient if you have just really so-called sparse data. One important thing with the row key is that rows are sorted lexicographically based on the row key. So designing the row key is very, very important for both for scalability when it comes to writing data, because the row key basically defines on which region server the data is stored. And it's also very important for your access patterns. So you should make sure that parts of the row key you query a lot is in front of the row key and not at the back, because they are sorted alphanumeric. So that's important. It's important design issue when designing an HBase model. All right. There are a lot of APIs available to access HBase data. There is, of course, the native Java, which is obviously the best. There is REST, Thrift, Avro, Ruby. We can access HBase data in a MapReduce, Chart, Hive. So there are a lot of API possibilities available to access data. For instance, in our project, we have a net-based application, and it's pretty easy to use the Thrift thing to have some kind of translator of client requests onto the native Java API. Well, and HBase itself is used a lot as well in Facebook, Twitter, Mozilla. The Mozilla store is pretty interesting because Mozilla is using HBase for storing their crash reports. I don't know if you have encountered a crash in Firefox, for instance. If you're gonna allow this to send this to Mozilla, that all data is crushed into HBase data. And if I'm not wrong, someone heard or read that about 300 gigabytes on data per day is going over here. So there is a lot of data coming along here. Crashes a lot. I don't know. So, NoSQL isn't the ultimate solution. Definitely not. It's not a drop-in replacement for your relational database, because there are no data types like we are used to. It's just a stream of bytes, just a byte array. So the values in there are just byte arrays. So what you have to do at the client is for both for writing and for reading data, you have the interpretation happens at the client. So the APIs usually have methods to convert byte arrays to native data types like integer or whatever. So there is no kind of query engine we know from Firebird. There is no optimizer there. You don't have joins or something like that. So there are no transactions actually, which allows you to work in an ACID way. Secondary indices besides your row key. So if you have a different access pattern where your row key isn't the optimal solution, then this one is a bit problematic as well. And you usually have to deal with denormalized data. So you usually have one fat table with the model to just put in qualifiers as you like without redefining the data model. So you basically end up with a denormalized data. But the thing is that compression, there are several compression options available. They work pretty well and now doesn't need any storage at all. So yeah. The perfect thing for HBase is if you really have key value pairs. So key value pairs means you have a key here, a key which you can uniquely identify a row, and pairs is not just a single value, but pretty much all you put into column families here and qualifiers. If you want to store something like that in a very large scale, HBase is really very good here. Scalability is one major thing with HBase, because if you suffer from scalability, so if you think that processing of data can be faster, you simply add more nodes to the cluster, and it automatically moves data to the new nodes and rebalance. And so scaling horizontally is pretty good here. It offers a very flexible data model, a very flexible schema, and yeah, well, I've already mentioned this with the null, and it supports both same structured and structured data. So you could also put structured data in there as well. All right, that's I could talk a whole day. About it, but I think that's a very short introduction into the world of Hadoop and HBase. So I don't know. Are there any questions? All right. Yes. Google's big table concept. You mean this one here? Yeah. The thing is that usually, yeah. The thing is that you usually have only one or two tables, one table, where you have your flexible schema to store data with inside a column family defined by a qualifier. So what you basically don't have to do is to join something. So that's one restriction, that you carefully have to design the row key here. So what you can do if you want to access data is either specifically access one row, yeah, or you can do some kind of range scan. So you can define a start row key and an end row key, and you get the result back. There are typically two use cases. What you have is either really you're interested just on a very small part of your data, then you pretty much go by a row key or a few row keys you want to select. Or you're doing a batch processing in a MapReduce job where you are processing a larger data because you have to pre-aggregate data or something like that, then it pretty much utilize the entire cluster. So there is no, with Hive is a project. Hive is a project which operates on top of HBase and allows you to formulate some kind of SQL style statements. But you have to use Hive for that. Any other questions? Okay. Well, let's talk about the case study a bit. Basically, it's a condition monitoring system in the domain of solar collectors and inverters. So it's typical to collect something like the current, the voltage, the temperature, and a lot of other data. So the thing here is that in the first concept, we had an expected data volume of 1,300 billions of measurement values per year. So there were estimations, for instance, if they sell 500,000 solar collectors, inverters in the world, they somehow have to deal with that. So the other thing besides data volume is that they really need a long-term storage solution. So it's not just a matter of storing the data for instance a week or a month or something like that. So for warranty and something like that, they really have to go back about, I think, 15 or 20 years on storing data, where all the data must not be that fast accessible, so they probably can move it to a smaller, to a slower medium, but they have to store it. They have one application, a web-based customer portal .NET web-based application, which are basically accessing detailed data directly from HBase, and they also have to deal with aggregated data. So, for instance, if they log in, the customer usually sees the aggregated data of the measurement values, daily aggregates over a day, over a month, or something like that, and he's able to click on a day, and for instance, then he sees the detailed values. So that's one requirement in respect to accessing the data. The idea is to have a lot of stuff going on at the back end, at the back office, with data analysis, data mining, machine learning, and fault detection. So there are a lot of things which they want to do with this amount of data. The initial problem was clear very quickly. We can't do it with a relational database system. So it's really impossible, even if you put in a lot of money into an Oracle cluster, you really can't manage that. So the thing is that measurement values in general are a very good example for p-values. So for p-value pairs. So what we did is we evaluated Apache Hadoop and HBase for storing this kind of detailed measurement values, and the results were pretty good. The tests were run on a virtualized Hadoop HBase test cluster with about 12 nodes. I think each node around 16 gigabytes of RAM and dedicated disk. So the one thing is the very small thing where the relational technology comes into the game here is now to store the aggregate data. Why should we store the aggregate data in a relational system? Because usually some kind of analysis things like data warehousing and such stuff is usually working on aggregate data. If you aren't interested in the detailed data, or if you don't need the detailed data, a relational system basically offers a much more richer way to access the data with any OL AP client like Excel, Vivo, or whatever. So that's rather hard doing with HBase. So the data model is pretty much the thing here. It's some kind of fixed length. So we have the data log ID. It's pretty much some kind of inverter here. So we have a device. The device can be some kind of sensor cards or something like that, and finally timestamp. So what we did is we defined the column families. They already are implementing the .NET-based application. They have an .NET object model already in place where they want to manage detailed data and something like that. So what we have to do here is to define HBase data model which basically maps directly to the object model here. What we did then is just to test the performance of the cluster and the scalability is we wrote data generators and data scanners to simulate writes, to simulate reads, and the result was pretty much that we are able to in a virtualized cluster, so not a physical one, that we were able to write about 70,000 rows per second, and the response time to get the detailed values out of HBase for one particular data logger device, so pretty much one data logger for a customer was around 400 simulated lines, lower than 150 milliseconds. So, and this all on at this time with a generated data volume of around 5 billion rows. What we did next is we implemented, we had to somehow get the aggregates out there, and what we did here is we implemented a MapReduce job on top of the MapReduce framework here. We basically end up with the following results here. We reached a throughput here of about 600,000 rows. I don't know. 600,000 rows per second. So a MapReduce job is pretty good in utilize an entire cluster. So you have to be very careful here because as I've mentioned earlier, with 12 nodes here, each having its own region server, each holding its own data and so on top of the distributed file system. There is a lot of going on in parallel here. So especially in the map phase where you read data, where you transform data, especially when you read data, all nodes can read data independently of the other nodes. So there's really a lot of going on. So what we've reached with our pre-aggregation MapReduce job here, we bumped up the database a bit with 15 billion rows, and we pretty much ended up with a full pre-aggregation over the entire set in about 7 hours. So including storing the about 70 million aggregated records in the relational database. Well, the thing here is I've mentioned a completely different data volume for 1 year. The thing is, of course we haven't the chance to test the entire expected data volume. So, but we are pretty sure, even if we haven't tested it, we are pretty sure that because of the scalability of such solutions, that it's really just a matter of adding more nodes. So if you think that your data volume grows and so on. You really have to expand your cluster, and you're pretty much done. Well, all right. Are there any questions? Yeah. The Roki?
Yeah, I mean.
This one here? This is our Sphinx. Sphinx in our case. Yeah, but they are compressed.
And what about you just use your Hadoop
yeah. That,
it's not your problem.
Correct. If we have a look here again, the distributed file system of Hadoop has some kind of replication factor. It's per default 3. So if you have data stored here somewhere with a replication factor of 3, it's basically anywhere here again 2 times. So you can pretty much lose 2 or something like that, and you should be fine. The thing is, for instance, with Google, they really have people just walking around and changing disks all the time because they are failing. Yeah, they are failing. So there is really things are failing here because the disks are one weak point here. But because of the nature of the distributed file system here with storing things redundantly, you pretty much it is fine, yeah. But I have to admit that I'm not in the administration stuff involved. I'm glad about that. So there are 2 really bright guys taking care of the test cluster. No, this hasn't yet, but they are really good in managing the cluster from an administration side. So we have been concentrating on the client side and developing things. Yeah. All right. Are there any other questions? Well, the last demonstration, as you might think of, I don't have a cluster with me, so what I can show you is that there is a Hadoop HBase distribution from Cloudera. Cloudera is a US-based company, and they really get currently a lot of money to move forward. So the distribution from Cloudera is pretty nice. So it basically does a lot of new things on top of the open source stuff which is available under the open source license. They pretty much package everything into one. Easy to use, easy to administrate, easy to monitor, and they provide 24/7 support and something like that. What you also get from Cloudera is an Ubuntu image with pretty much having one VMware session, one node, running everything you need just to get started, to start developing. So that's really convenient that you don't have to deal with installing on Linux and something like that if you are not used to simply try things here. So what I'm going to show you here is the aggregator. So we have we have a few tables here, and I think I just want to use one here. Okay. Sadly enough, I had resumed the VMware, and now some processes aren't running. So I have to reboot the VMware. I'm not doing this right now. Basically, the result is what you get in the database is that we have I think what we have here is we have simply one table storing the aggregated data. Well, sorry about that. It doesn't work. The thing is, if we want to have a quick look in the MapReduce job implementation, is that there are basically the things we are going to do here is we have the map phase. Well, it's in Java. It's the map phase. So the map phase pretty much reads data records from the HBase table, and this is done in you have to override here a so-called map method. And what you do here is you read data, you iterate over data, transform it in a way that it's the row key isn't the row key for detailed value anymore, but for a daily aggregated data. So basically, the row key pretty much cuts off the time part of the timestamp. The next thing is if things are read, then it goes into a so-called combiner. A combiner is pretty much, if you remember the MapReduce framework, the combiner is pretty much a reducer, but the combiner uses the so-called data locality. So the combiner always operates on data locally to the region server the combiner is currently running. So there is no, in this step, there is no network traffic involved. So once the combiner is done, once the local reduce operation is done, it's gonna get to the so-called global reducers. So global reducers are pretty much receiving data from the combiners and finally generate the result. And the thing here is that the magic here is that with all the plumbing codes, you need to set up a MapReduce job to define the inputs, define the output, that basically with the context.write call here in the reduce phase, data is actually written into the output format. In our case, it's it's database output format, a relational database output format. We had a few problems here with there is an output format called DB output format. We had a few problems with that, so we ended up with writing our own output format for Firebird and Oracle, which is rather simple. It's just expanding the existing DB output format and writing some code here. It uses gdbc batching, so batch operations with optional commit interval, optional batch size values. So we have tried here to optimize in respect to storing data in the relational database where we can. So basically that's all. I'm sorry for not running the MapReduce job, but I think it's just a matter of seeing the progress or something like that. So, all right, thanks very much for your attention. If you have any questions, feel free. All right, then